So what I've suggested is that we should also consider cos theta in terms of the adjacent divided by the hypotenuse, the relationship between these two sides in the angle. For these, what I would argue are popular angles to recall. And notice that when we do divide by 2 to aid in that concept, to aid in the memorization of it, because it produces a lovely little pattern of root 0, root 1, root 2, root 3, root 4 to recall, the next stage from there is to simply then simplify it down and then have a discussion as to what this represents in terms of cos theta's value of adjacent divided by hypotenuse. So first of all, root 4 is 4. So again, this is a circumstance where you have 2 divided by 2, which would give you the concept of 1 as your answer here. And then you have root 3 over 2, root 2 over 2, 1 over 2 for 60 degrees this time relative to 30, and 0 at 90 degrees. And so what we can say is the simplified way of visualizing how cos theta behaves. That is to say, how is it that cos theta produces outcomes or values of heights for certain degrees, and for these, what I judge to be important angles, we can see that the height of if I go in this pattern, the height of the adjacent or the length of the adjacent drops as the angle goes up to 90 degrees. It goes all the way from root 4 all the way down to root 0, and there's a way that we can visualize this. These values, because I've simplified it down to no longer include the 2 over 2, and this one is just 0 rather than root 0 or 0 over 2, these will now be considered just the value of cos theta. What is the output or the range values that come out of cos theta? But remember where they have come from. They've come from a decision to choose the length of the hypotenuse. Okay, let's move on. So let's make sure this is visible. And one way we can do that is we can take a look at some triangles. I'm going to place my triangle slightly differently, upwards, wherein these, if that is a good enough description, vertical from this point, wherein that length is the adjacent side, and you can see therefore that this length would be the hypotenuse that I've considered to always be 2. So it is 2 there, not drawn to scale is 2 there, and if I move to over here, that is also 2. The difference, however, now is the adjacent side for 30 degrees produces this right angle triangle, and we can see that quite comfortably. That is the basic right angle triangle for 30 degrees, assuming that this is a value of 2 and that it's staying constant. Now notice root 3 is about 1.73, so it's oversimplification, but their adjacent side is about 1.73. Notice that's what we got for 30 degrees. Root 3 is the adjacent, 1.73, and the hypotenuse is 2. For 45 degrees, because what you ended up with is a movement from here to here, and it curled from movement from that position down as the angle increased by 45 degrees. So instead of it being this tall, as the angle went round this position here, so as the angle went round in that corner, you ended up with a circle-like structure, moving it down, changing the length of the adjacent to only 1.4 root 2. Finally, for 60 degrees, we can say the same. By the time I get to 60 degrees, the adjacent length is only 1, hence 60 is 1 over 2. 45 is root 2 over 2, and 30 degrees is root 3 over 2. So let's put that into context. If you can map this out by suggesting that you fit it into a circular-like object. Here, 30 degrees with an adjacent of root 3. 45 degrees has moved on. It has moved from here to here. It has moved on, round from there, 45 degrees. From 45 degrees from 30, so it's gained an extra 15 degrees, and as so it moved round that circle. Additionally, as I go to 60 degrees, you can see that at the 60 degree point, I will be all the way at this point in the circle, and notice how my adjacent is shrinking with every step. My adjacent has gone down as my angle goes round.